Hello and welcome back. In this lecture, we're going to learn about a different loss, a different one from the losses that we've been learning before, like the cross entropy and the binary cross entropy and all of these other losses that we've been learning before. And this different type of loss is called the contrastive loss. Now, this loss is used to measure the distance or the similarity between two inputs. So these inputs, for example, can be images. As you can see here, we have two images. And we want to measure how similar these two images are. So in this case, these two images are very similar because they're from the same person. So we encourage their distance to be small. So this loss will minimize the distance between these two images since they're the same. And if they're different images, so here they're different people. These two people are different. So we encourage the distance to be large. Okay, because we want the model to predict that these two images are not similar. So let's dive deep into the contrastive loss. So as we said before, it's a distance-based loss as opposed to the prediction error-based loss, like the cross-entropy loss that we've been talking about previously, or the other loss functions such as the binary cross-entropy, the mean squared error, and so on. These are all called the prediction error-based losses. Okay, so this is different. It's called the contrastive loss, and it's a distance-based loss. So it measures the distance between the inputs. And it's used to learn discriminative features for images. So whenever you want to encourage discriminability of your inputs, then one very good option is to use the contrastive loss. So what it does is that it ensures semantically similar inputs are embedded closer together because it's going to minimize the distance between them. And whenever you have dissimilar inputs, then you want to ensure that the distance between them is maximized. So this loss measures the similarity between the two inputs you provided. If your inputs are images, then it measures the similarity between the two images. Now, you've realized something, that each sample is actually a pair. So each sample is composed of two images. Now, you can have a positive pair and a negative pair. A positive pair is when the two images are from the same class, or the two images are similar. So here we have images of a person, and they're actually the same person, just a different appearance. So this is a positive pair. And here the images are from a different person, so this is called a negative pair. Okay, so the sample is actually a pair. So we have two images, and this is a positive pair, this is a negative pair. And what we want to do is minimize the distance between the positive pair and maximize the distance between the negative pair. So this is basically what's written here. We want small distance between the positive pair because they are similar images, and great distance, then some margin m for negative pairs. And we're going to talk about the margin m in the next slide. So this is the loss function. This is the equation for the loss function. First of all, let's visualize the diagram here. So when your inputs are when your inputs are images, so you feed in this sample. Again, a sample is composed of a pair. So you feed it to the same network. Realize that these two are not different networks. They're basically the same exact network, same weights. So you're feeding each pair to the network, and you're extracting some features. And then what you're going to do is you're going to use these features OX1 from the first image and OX2 from the second image, and you're going to use these features to compute the contrastive loss. And then this loss is going to tell us if these inputs are similar or dissimilar. So let's see how it does that. This is the equation. So the equation is y times d squared. D is the distance, and 1 minus y times the maximum between the margin minus the distance and 0. So let's break it down. First of all, d is basically the distance between the two images. How can we calculate the distance? Is by taking the Euclidean distance of the image features. So remember, the image features for the first image we have OX1 and OX2, and basically if we calculate the Euclidean distance, that means we're just going to subtract them from each other, square them, and take the square roots at the end. And this will compute the Euclidean distance between the two image features. So this is basically what d is right here. Now, y here is the actual label. So y equals 1 when the two images are similar, and 0 when the two images are dissimilar. So in this case, we have a positive pair because the two images are similar. They're from the same person. So our label should be 1 in this case. Now, when we have dissimilar images, like the image on the right here, then the label in this case should be 0. So what happens here when you plug, let's say first of all, in the first case, that the images are similar. So we have positive pairs. So what happens? The label is 1 because the two images are similar. So y equals to 1. Let's plug in y here. Let's substitute y with 1 and see what happens. So when you substitute y equals to 1 in this equation, you'll basically only get this term. Because if this is 1, then 1 minus 1 is 0, and basically this whole term goes away, and you'll just end up with d squared. So in this case, when the images are similar, you want to minimize this distance. So if the network predicts a very big distance between these two images, you're going to have a high loss. Again, you're squaring this loss. And in this case, you have a high loss, so your network tries to minimize it. So let's say after training, you have a good model. And what happens here is that the two images here are, when you calculate the distance between them, then you'll get a small distance. So at the end, you'll get a small loss. So let's say you get a distance of 0.2. When you square 0.2, you'll get 0.04, which is a small loss, so your network is performing good. Okay, now let's look at the other case, which is when these two images are not similar. So when these two images are not similar, then y equals to 0, right? So this term cancels away because you're just multiplying 0 times d, so this whole term cancels away, and you'll end up with this term right here because y is 0, so 1 minus 0 is just 1, so basically you're just ending up with this term, which is the maximum between the margin minus the distance and 0. So let's first of all explain what the margin is here. So the margin is used for confidence. If two images in a pair are dissimilar, then their distance should be at least margin, okay? Or a loss will be incurred. So in this case, the network doesn't only penalize wrong predictions, but it also penalizes correct predictions that are not confident enough. So whenever you introduce the margin, then you're ensuring that dissimilar inputs are very far away from each other. And this is exactly what we want here. We want the dissimilar inputs to be far away from each other, at least by this margin m that we're introducing here. Okay? So this is, again, to introduce discriminability. If you want to take it as an example, then imagine we have two images, one of a jaguar and one of a leopard. So what you want to do is you want to train the model to discriminate between these two images. And as you can see, these two images are very similar to each other. So if you don't introduce the margin, then your model might predict that these two images are similar. But when you introduce the margin, that means you're ensuring that these two images are at least far away from a margin that we're defining. So this is if you want to take it as an example. Maybe this example would be quite hard for the model because they're very alike, even though they still have some different features. However, the global context is still very similar. So this is the objective of using a margin. So in this case, when does the loss become 0? When the distance is bigger than the margin. Okay, because when you're subtracting a number from a smaller one, then you'd have a negative. So then we're going to take the maximum between the negative value and 0, and of course the maximum is 0, so therefore you'd end up with a loss of 0. So the loss becomes 0 when the distance is bigger than the margin. And that's, again, the objective of using the margin. So during training, an image pair is fed. So this is the pair of images here. So this is one sample. We feed this sample and the labels, okay, which is 1 or 0. 1 if the images are similar, and 0 when the images are different. So that's basically it for the contrastive loss. And one more thing before we end this lecture. If you refer to the paper where they talk about the contrastive loss, then you're going to find this equation right here, which is very similar to the equation that we discussed, except that they use half of the distance squared. So why is half? Is that when you're deriving the distance, okay, so when you derive d squared, then you'll just get 2d. Okay, so the 2 gets cancelled with the 2 right here, and you just end up with the distance. So they've included the half here and here in both terms. And another difference is that y is 0 if the inputs are the same, and 1 if the inputs are not the same. So it's the opposite of what we discussed here, but it doesn't really matter. It just depends on how you supply the labels. Just make sure to supply them all in consistency. So you need to be consistent. If you decide that you want 1 to be for the same images and 0 to be for the different images, then you have to be consistent. Do that for the whole training set. And if you decide that 0 should be for the similar images and 1 should be for the different images, then you also need to be consistent within your for your complete training sets. So if you read the paper, you're gonna see these two differences. Okay, there's two papers: Siamese networks for one-shot image recognition and dimensionality reduction by learning and invariant mapping. There's other papers that also discussed the contrastive loss, but it's enough to read these two papers if you want to learn more about it. So that's it, and I'll see you next time.